Physics 2, Lab 3, Circuits by Swam Sankit Kumar Trivedi. Introduction. Purpose. By applying the principles of energy conservation and charge conservation, this lab will predict the behavior of resistor networks in series and in parallel. It will measure actual current and voltage values using digital multimeters, investigate the characteristics of ohmic resistors and the charging-discharging behaviors, and it will graph the results on Excel. The fundamental principles used are node rule, which basically says at any circuit junction, the sum of currents entering equals the sum of currents leaving. Loop rule, which in any closed circuit loop, the algebraic sum of the voltage drops and rises is zero. And Ohm's law, where the voltage across a resistor equals the current in it times the resistance. The preview of the main results is Kirchhoff's law remain valid and the exponential time dependence of current. In this slide, I have better explained the main physics ideas used and the formulas in order of what I was talking about. The system in this experiment was the circuit, while the surrounding was everything else. I then simulated the circuit into a website online and through my calculations, I was also able to find that the current passing through each of the resistors is 0.0204. And this is proven by the online simulation too. So the first experiment was if we reversed an ammeter, what exactly would happen? And the truth is, nothing really happens. Moving on to experiment 2. What if instead of reversing the ammeter, we replaced it with a voltmeter? Well, in this case, two things happen. Firstly, the ammeter reads 0 amps. This is because the voltmeter's internal resistance is extremely high, which is virtually no current can flow through that branch of the circuit. So the ammeter registers 0 amperes. And the second is we see that the voltmeter reads 3 volts. So if no other component drops in the series in terms of voltage or resistance, then the entire supply voltage appears across the meter. Hence, due to the formula V is equals to IR, and if we rearrange it, we get and plug in the values, it gives us the full 3 volts. Because we know the current flowing throughout the circuit, we can find the voltage drop in each component of the circuit. And according to the loop rule, the sum is equal to 0. So with the three terms, as the voltage change in VAB, change in VCD, and change in VEF, the voltage drop rises, and we can calculate and see that the net charge is 0 volts. So towards the left hand side, we can see the graph of how exactly this voltage changes. So why is there no change in the ammeter reading? So the graph validates the loop rule, which I showed on the previous page, and the ammeter reading stays constant because the voltmeter's extremely high resistance draws negligible current, so it doesn't alter the circuit's current or electron flow. Experiment 5. What if we replace the voltmeter with ammeter in parallel? The ammeter's near zero initial resistance efficiently bypasses the 100 ohm resistor, which reduces the total resistance to around 47 ohms. So applying Kirchhoff's loop rule, we can see that the current will become approximately 0.06 amps. So resistance in each component. So using Ohm's law or rearranged, basically R is equals to V over I, we can see that for the 47 ohm resistor, it was approximately 48 amps. For the 100 ohm resistor, it was 102 amps. And for the connected wire, it was 0 amps. And for the ammeter, it was around 0 amps too. Moving on to RC circuits, during charging and during discharging, the amount for 10 ohm resistor, it took around 10 seconds to charge and discharge, while for a 20 ohm resistor, it took 20 seconds to charge and discharge. These are the results I got for the RC time constant for 9 voltage battery, and the predicted RC was 6 and the experimental RC was 6.879. Throughout this experiment, there could have been a range of possible errors. One error includes timing inaccuracies from human reaction delay, which simultaneously stops the stopwatch and isolating the capacitor's discharge. The second error is discrepancy between online simulations and physical experiments due to unmodeled real-world factors and component tolerances. What if? How would a real ammeter's finite internal resistance affect our measurements? Even a high quality ammeter has some initial resistance. When placed in series, this extra resistance reduces the total circuit's current slightly, so the reading isn't exactly the ideal value. And what happens if we connect the real battery directly to a capacitor with no resistance? Without a resistor, our model predicts the capacitor will discharge instantaneously. In reality, a battery's internal resistance limits the charge rate. Thank you.